Look up at the night sky. What do you see? A scattering of stars, maybe a planet or two, the faint glow of distant galaxies. But here's the thing, what you're seeing is just the surface. Beneath it all lies a hidden architecture, a cosmic blueprint so intricate and vast that it defies everything we thought we knew about reality. For centuries, we've wondered how the universe works, but only now, with the power of advanced astrophysics, are we finally peeling back the layers to reveal its deepest secrets. And what we've found, it's stranger, more beautiful, and more mind-bending than anyone could have imagined. Think about this. Every atom in your body, every planet in our solar system, even the light from the farthest galaxies, all of it is governed by invisible forces and structures we're only beginning to understand. Dark matter, an elusive substance that makes up most of the universe's mass, bends space itself like an unseen hand shaping the cosmos. The cosmic web, a vast network of filaments connecting galaxies across billions of light years, acts as the universe's skeleton, holding everything together in a delicate balance. And then there's dark energy, a mysterious force pushing the universe apart at an ever-increasing speed. These aren't just abstract ideas, they're the very framework of existence, and they're rewriting the rules of physics as we speak. So why does this matter to you? Because these discoveries aren't just about distant stars or abstract theories. They're about us, our place in the universe, our future among the stars, and the fundamental questions that have haunted humanity since the dawn of time. What is the universe made of? How did it all begin? And where is it all heading? Over the course of this journey, we'll uncover 30 of the most astonishing secrets of the universe's architecture, each one a piece of the puzzle that brings us closer to answering those questions. From the quantum fluctuations that seeded the first galaxies to the mind-bending possibility of parallel universes, we're about to explore the frontiers of knowledge, and trust me, you won't want to miss a single revelation. So let's dive in, because the cosmos has been waiting billions of years to share its secrets, and today we're finally listening. Picture the universe not as a vast emptiness dotted with isolated galaxies, but as a living, breathing network, an intricate tapestry woven from threads of dark matter and glowing gas. This is the cosmic web, the hidden scaffolding that holds everything together. Scientists once thought galaxies floated alone in the void, but now we know they're just knots in this grand design, strung along filaments like pearls on an invisible string. These threads stretch mind-boggling distances, some longer than you could travel at light speed in the entire history of human civilization. What's astonishing is how we discovered this celestial architecture. Astronomers used gravitational lensing, nature's own magnifying glass, to detect the subtle way these filaments bend light from distant objects. Supercomputer simulations then brought the web to life, showing how dark matter, that mysterious, invisible substance, acts as the framework, while ordinary gas flows along it like water through pipes. Where these cosmic rivers intersect, galaxies form in dazzling clusters, drawn together by the web's gravitational pull. Here's what flips everything we thought we knew on its head. This web didn't just appear fully formed. It grew from tiny quantum fluctuations in the early universe, stretched into existence by the relentless expansion of space itself. Those microscopic wrinkles in time eventually became the seeds for galaxy clusters, with voids between them so enormous they could swallow thousands of Milky Ways. This means the universe has a memory, a fossil record written in the distribution of galaxies we see today, and the implications, they're staggering. The cosmic web explains why galaxies move in unexpected ways, why certain regions of space seem emptier than they should be, and even hints at how dark energy might be stretching this web apart over cosmic time. It's like finally seeing the girders inside a skyscraper after only ever observing the windows suddenly. The whole structure makes sense. Every time we map another section of this web, we're not just charting space, we're reading the story of how reality organized itself from chaos into the breathtaking cosmos we call home. We've mapped galaxies, calculated cosmic expansion, even recreated the birth of the universe in supercomputer simulations, yet 27% of everything that exists remains utterly invisible to us. This is dark matter's invisible dominion, the unseen scaffolding that shapes the cosmos. Picture a puppeteer pulling strings in complete darkness. We only see the dance of galaxies, never the hands guiding them. Without this mysterious substance, spiral arms would unravel, clusters would disintegrate, and the night sky would be an unrecognizable void. What makes dark matter so baffling isn't just its invisibility, it's how differently it behaves from everything we touch and see. While ordinary matter clumps into planets and stars, dark matter forms vast, diffuse halos around galaxies. When two galaxy clusters collide, astronomers observe something eerie. The visible gas smashes together and slows down, while the bulk of the mass revealed through gravitational lensing glides right through itself like ghosts passing through walls. This proves dark matter particles don't interact with light or each other the way atoms do. They're cosmic phantoms felt only through their gravitational whisper. The hunt to identify these particles has spawned some of humanity's most ambitious experiments. Deep in abandoned gold mines, ultra-sensitive detectors wait for the once-in-a-lifetime moment a dark matter particle might bump into an atomic nucleus. The Large Hadron Collider smashes protons together at near light speed, hoping to create dark matter in miniature cosmic collisions, even more astonishing. Some theories suggest dark matter might be part of an entirely hidden sector of particles and forces, a parallel universe of physics right under our noses. Here's what's truly humbling. Every alternative theory scientists have proposed modified gravity, extra dimensions, even flaws in Einstein's relativity crumbles when faced with the mountain of evidence. From the way galaxies rotate to the bending of light around galaxy clusters, only dark matter explains all the cosmic puzzles. It's not just holding the universe together, it's holding up our fundamental understanding of physics. And when we finally catch it, we won't just be discovering a new particle. We'll be opening a door to 95% of reality we've never seen before. Just when we thought we understood the universe's expansion, that after the Big Bang, everything should gradually slow down under gravity's pull, astronomers stumbled upon something that shattered that assumption. In the late 1990s, two independent teams studying distant supernova made the same shocking discovery. The universe isn't just expanding, it's accelerating, as if some invisible force is pressing harder on the cosmic gas pedal with each passing moment. This mysterious driver, dark energy, an enigma that makes up a staggering 68% of everything in existence. Here's what makes dark energy so perplexing. While gravity pulls matter together, dark energy does the opposite. It pushes space itself apart. Imagine blowing up a balloon with tiny dots representing galaxies. Now picture the balloon inflating faster and faster on its own, not because you're blowing harder, but because the rubber itself has some strange property causing it to stretch more aggressively over time. That's dark energy's effect on the fabric of reality. The farther apart two galaxies are, the faster this phantom force drives them apart, meaning distant regions of space will eventually vanish beyond an unbridgeable horizon, lost to us forever. The leading theory, Einstein's cosmological constant, a sort of background energy woven into space itself. He originally proposed it as a mathematical fudge factor to keep the universe static, then called it his greatest blunder when expansion was discovered. But now it's back in vogue as a possible explanation for dark energy's relentless push. There's just one problem. Quantum physics predicts this energy should be unimaginably stronger than what we observe, off by a factor of 1 followed by 120 zeros. It's like expecting a hurricane and feeling only a faint, inexplicable breeze. Alternative ideas are even wilder. Some physicists propose quintessence, a dynamic field that evolves over cosmic time, its strength waxing or waning. Others suggest our three-dimensional universe might be brushing against hidden extra dimensions, leaking gravitational force in ways that mimic dark energy's effects. Then there's the radical possibility that Einstein's theory of gravity itself needs rewriting on cosmic scales, that what we're seeing isn't a new force at all, but gravity behaving differently across vast intergalactic distances. What's at stake isn't just academic curiosity. Dark energy determines the universe's ultimate fate. If it strengthens over time, it could rip apart galaxies, stars, even atoms in a catastrophic big rip. If it weakens, gravity might regain control, collapsing everything back into a fiery crunch. Or it might continue its steady push, leading to a cold, dark, lonely cosmos where distant civilizations are forever isolated. Every measurement of supernova, galaxy clusters, and the cosmic microwave background brings us closer to answering these existential questions, not just about the universe's architecture, but about our place within its unfolding story. Zoom in far enough, past atoms, past quarks, down to scales a billion times smaller than a grain of sand, and the smooth fabric of space-time dissolves into a seething, crackling chaos. This is quantum foam, the universe's most fundamental layer, where reality itself boils with fleeting particles and wormholes that flicker in and out of existence like bubbles in a cosmic soda. At these unimaginably tiny distances, space-time isn't the calm, predictable stage Einstein envisioned. It's a turbulent storm where the very concepts of here and now lose all meaning. The idea emerged when physicists tried merging quantum mechanics with gravity, down at the Planck scale, where distances shrink to 10 to the power of -35 meters. Heisenberg's uncertainty principle wreaks havoc. Energy fluctuations so violent they can briefly warp spacetime itself, erupt from nothingness, creating a froth of virtual black holes and tunnels that might connect distant parts of the universe. Picture the ocean's surface during a hurricane. What looks smooth from a satellite reveals violent churning up close. Quantum foam is that storm, but for the fabric of reality. What's mind-bending is how this chaos leaves fingerprints we might actually detect. Some theories suggest ultra-high-energy cosmic rays particles hurtling through space with energies millions of times greater than anything our particle accelerators can produce, could interact with quantum foam as they travel billions of light years. If spacetime were perfectly smooth, these rays would arrive at Earth with predictable energies. But if they've been jostled by microscopic spacetime bubbles along the way, their energy signatures might carry telltale wrinkles like a photograph slightly blurred by passing through frosted glass. The stakes couldn't be higher. Quantum foam isn't just academic curiosity, it's a battleground for physics itself. Einstein's relativity paints spacetime as a smooth, bendable sheet, while quantum mechanics insists everything, even empty space, must be granular and uncertain. Reconciling these visions could unlock the long-sought theory of quantum gravity, a framework to explain everything from the Big Bang to black holes. Some models even suggest quantum foam might allow time travel at microscopic scales, with causality itself breaking down in the foam's frenzy. Yet for all its wild implications, quantum foam remains tantalizingly just beyond our reach. Current technology can't probe these scales directly. It's like trying to measure the ripples in a pond with a ruler a mile long. But as astronomers collect more data from cosmic rays and physicists push particle detectors to new extremes, we're inching closer to glimpsing this primordial turbulence. And when we do, we won't just be seeing the universe's smallest structures. We'll be staring into the seething cauldron where space, time, and perhaps even new dimensions are born. Black holes have always been cosmic enigmas, regions where gravity is so intense that not even light can escape. But here's where it gets truly bizarre. According to Stephen Hawking's groundbreaking work, black holes aren't eternal. They slowly leak energy, emitting what we now call Hawking radiation, fading away over unimaginable eons. But this revelation created a paradox that has haunted physicists for decades. If a black hole vanishes, what happens to all the information it consumed? Every star, planet, or spaceship that fell in carried quantum information, detailed blueprints of its existence. If that information is lost forever, it violates a fundamental law of quantum mechanics. Information can never be destroyed. This contradiction, known as the black hole information paradox, has sparked one of the fiercest debates in modern physics. On one side, Einstein's general relativity insists that whatever crosses the event horizon is gone for good, shredded into oblivion. Quantum mechanics, on the other hand, demands that information must persist, even if scrambled beyond recognition. For years, it seemed like the two foundational theories of physics were locked in an irreconcilable battle. But recent breakthroughs might finally offer a way out. Enter the holographic principle, an idea so radical it rewrites our understanding of reality itself. Imagine a black hole's event horizon not as a one-way door to destruction, but as a two-dimensional surface encoding everything that falls inside, like a cosmic DVD. According to this theory, the information isn't lost, it's imprinted on the horizon in vanishingly small pixels, each barely larger than the Planck length. As the black hole emits Hawking radiation, it slowly releases this encoded data back into the universe, like a scrambled message gradually revealing itself. String theory takes this even further. Some models suggest that black holes are tangled knots of vibrating strings, with their event horizons acting as holographic screens. When matter falls in, it doesn't disappear. It's transformed into a frenzied dance of strings on the surface, preserving every quantum detail. This means the three-dimensional reality we perceive might be a projection of information stored on distant two-dimensional boundaries. It's as if the universe is running an unimaginably complex simulation, and black holes are its data compression units. The implications are staggering. If information truly escapes black holes, it means reality is far more resilient than we thought. It also hints at a deeper unity between quantum mechanics and gravity, a bridge between the very small and the incomprehensibly vast. Experiments with quantum computers and simulations of holographic systems are now testing these ideas, searching for echoes of this cosmic data preservation. What's at stake isn't just theoretical elegance. Solving the information paradox could unlock the secrets of quantum gravity, reveal the true nature of space-time, and even answer whether our universe itself might be a hologram. Every time a black hole flickers out of existence, it's not erasing reality, it's challenging us to decode the universe's most profound mysteries. And with each new discovery, we're one step closer to understanding how information, the most delicate and enduring thread of existence, weaves the fabric of the cosmos together. What if everything you see, the stars, the planets, even your own hands, isn't truly three-dimensional? What if it's all an illusion, a holographic projection from a two-dimensional surface at the edge of the universe? This isn't science fiction. It's the holographic principle, one of the most radical ideas in modern physics, and it's shaking our understanding of reality to its core. The story begins with black holes, those cosmic vacuum cleaners that swallow everything in their path. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, a measure of its hidden information, isn't determined by its volume, as you'd expect, but by the surface area of its event horizon. It was the first hint that the universe might encode information in unexpected ways. Fast forward to the 1990s, when physicist Leonard Susskind and Nobel laureate Gerard T. Hooft took this idea even further. They proposed that all the information contained within a region of space, every particle, every force, every whisper of energy, could be perfectly described by data stored on its boundary, like a cosmic projector screen. Here's where it gets truly mind-bending. Imagine the entire universe as a giant sphere. According to the holographic principle, everything happening inside that sphere, galaxies colliding, stars being born, even your thoughts, could be represented by bits of information painted onto its outer surface. It's as if the three-dimensional world we experience is just a shadow cast by a deeper, two-dimensional reality. Think of it like a credit card hologram. Tilt it, and a 3D image appears, but at its core, it's just a flat, encoded surface. But how could this possibly work? The mathematics behind it comes from string theory, where vibrating strings at the universe's boundaries create the illusion of depth through their interactions. Some versions even suggest that spacetime itself emerges from quantum entanglement, those spooky connections between particles that Einstein famously disliked. The more entangled particles are across a surface, the more solid and three-dimensional the space within it appears. It's like realizing the movie you've been watching isn't filmed in 3D at all. It's an incredibly convincing trick of light and math. The implications are staggering. If the holographic principle holds, it could solve some of physics' biggest puzzles, like how to reconcile quantum mechanics with gravity. It might even explain why the universe appears finely tuned for life, because the real rules governing reality operate in a simpler, lower-dimensional realm. Experiments are already underway to test these ideas. Fermilab's holometer, for instance, is searching for telltale pixelation in space-time tiny fuzziness that would betray the universe's holographic nature, like detecting the individual dots on a TV screen up close. Critics argue that the principle remains untested, and some interpretations border on metaphysics. Yet its mathematical elegance keeps drawing physicists deeper into the mystery. Whether the universe is truly a hologram or not, this idea has already reshaped how we think about information, space-time, and the very nature of existence. It reminds us that reality might be far stranger and far more interconnected than we ever imagined. And if the holographic principle is correct, then every galaxy, every atom, every moment of your life is just one breathtakingly complex projection from the edges of the cosmos. One moment, the universe was smaller than a single atom. The next, it exploded outward faster than light itself could travel, not just expanding, but stretching space so violently that a region the size of a marble ballooned to the scale of our observable cosmos in less than a trillionth of a second. This is cosmic inflation, the most dramatic growth spurt in existence, and it solves mysteries about our universe that baffled scientists for decades. Before inflation theory, astronomers struggled to explain two puzzling observations. First, why is the universe so remarkably uniform? Look in any direction, and the cosmic microwave background, the afterglow of the Big Bang, shows nearly identical temperatures, as if opposite ends of the cosmos had once been neighbors. Second, why is space so flat? General relativity allows for curved universes, yet every measurement suggests space-time is as level as a sheet of glass across billions of light years. Without inflation, these facts made no sense. Distant regions of space should never have had time to equalize temperatures, and the universe's density should have curved space dramatically over time. Here's the breakthrough. Inflation acted like a cosmic iron, smoothing out wrinkles and flattening space by stretching it so unimaginably fast that quantum fluctuations became the seeds for galaxies. Picture blowing up a balloon covered in tiny dots. As it inflates, dots that were once close together rush apart, while the balloon's surface appears flatter and more uniform at larger scales. Inflation did this to the entire universe, but instead of air, it was driven by a mysterious energy field that briefly dominated reality, pushing space apart with unimaginable force before vanishing almost as suddenly as it appeared. The smoking gun ripples in space-time itself. Inflation's violent expansion should have generated gravitational waves, undulations in the fabric of reality that left faint imprints on the cosmic microwave background. Experiments like BICEP and the upcoming Lightbird satellite are hunting for these primordial fingerprints. If detected, they'd provide direct evidence of inflation and offer clues about the energy field that powered it. Some theories even suggest inflation wasn't a one-time event, but part of an endless cycle where new universes constantly bud off from others in a vast multiverse. What's astonishing is how such a brief event shaped everything we see. Without inflation, galaxies might never have formed, and the universe could have collapsed back on itself or torn apart too quickly for stars to ignite. That split-second expansion fine-tuned reality, setting the stage for cosmic structures to emerge billions of years later. It's humbling to realize that the vast web of galaxies, the planets orbiting distant suns, even the conditions that allowed life to arise, all trace back to a blink of time so short, no clock could measure it. Yet in that instant, the universe wrote the blueprint for its own destiny. Every particle of matter in the universe has an evil twin, an antimatter counterpart identical in mass but opposite in charge. When matter and antimatter meet, they annihilate in a burst of pure energy. According to all known physics, the Big Bang should have created equal amounts of both, leaving behind nothing, a universe of empty space. Yet here we are, surrounded by galaxies, planets, and atoms, proof that somehow, someway, matter won the ultimate cosmic showdown. This mystery, known as Baryon asymmetry, is one of physics' greatest unsolved puzzles, and the answer might rewrite our understanding of existence itself. The plot thickens when you consider how perfectly balanced matter and antimatter should be. Every particle collision we observe in labs produces them in equal pairs, like a cosmic seesaw that never tilts. Even subtle differences in their behavior could explain why matter dominates, but for decades, searches came up empty. Then came the breakthrough. Neutrinos, those ghostly particles that barely interact with anything, might hold the key. Experiments like Japan's Super Kamiok and China's Jiangmen Underground Neutrino Observatory are hunting for a phenomenon called charge parity violation, a tiny quirk where neutrinos behave differently than their antimatter counterparts. If neutrinos violate these symmetry rules more dramatically than other particles, it could explain how a slight excess of matter survived the early universe's annihilation frenzy. Particle colliders are chasing another clue. At CERN Large Hadron Collider, scientists recreate the searing conditions of the early cosmos, watching for rare instances where certain particles decay slightly more often into matter than antimatter. One prime suspect is the hypothetical right-handed neutrino, a heavier cousin to the known neutrinos that might have tipped the scales in matter's favor. There's also the possibility of undiscovered forces that treated matter and antimatter differently during the universe's first fractions of a second, forces that vanished as space cooled, leaving behind only the faintest traces in today's particle interactions. What's astonishing is how fine-tuned this imbalance had to be. If matter had outnumbered antimatter by just 1 part in a billion less, there wouldn't have been enough left after annihilation to form galaxies. 1 part in a billion more, and the universe might have collapsed under its own density before stars could form. It's as if the cosmos threaded a needle so precisely that the very existence of complex structures and life itself depends on that microscopic asymmetry. The implications go far beyond particle physics. Solving Baryon asymmetry could reveal whether our universe is just one bubble in a vast multiverse, where other regions might be dominated by antimatter. It might even expose hidden connections between the quantum world and the large-scale structure of spacetime. Every time a neutrino detector registers a flicker of light or a collider smashes particles at near light speed, we're not just probing the origins of matter, we're uncovering the reason anything exists at all. And that answer, when we find it, will rewrite the story of our cosmic beginnings from its very first line. They slip through your body by the trillions every second, ghostly particles born in the hearts of stars, the fury of supernova, even the radioactive decay of rocks beneath your feet. Neutrinos barely interact with matter, passing through entire planets like they're not even there, but don't let their shyness fool you. These elusive particles hold a cosmic secret. They shape the universe in ways we're only beginning to grasp, and their ability to shape-shift mid-flight, a phenomenon called neutrino oscillation, might rewrite our understanding of mass, energy, and the fate of the cosmos itself. Picture a neutrino leaving the sun's core. Born as an electron neutrino, it begins its journey to Earth, but by the time it reaches us, something strange happens. It's no longer the same particle. It's morphed into a muon or tau neutrino, trading identities like a cosmic undercover agent. This metamorphosis, first confirmed in the late 1990s, shattered decades of assumptions. Neutrinos weren't massless after all. However tiny, their mass bends spacetime, adding gravitational glue that helps sculpt galaxy clusters and accelerates dying stars' explosive final acts. The implications ripple across astrophysics. When a massive star collapses into a supernova, 99% of its energy isn't blasted outward as light. It's carried away by a tsunami of neutrinos. These particles act as invisible sculptors, shaping shockwaves that determine whether remnants become neutron stars or black holes. Deep beneath the South Pole, detectors like Ice Cube, a cubic kilometer of ice studded with sensors, capture these ghostly messengers. By tracking their flavors and energies, scientists reconstruct stellar explosions millions of light years away, piecing together how neutrinos influence the universe's chemical makeup. But here's the real twist. Neutrino oscillations hint at physics beyond the standard model. Their tiny masses don't fit neatly into existing theories, suggesting undiscovered particles or forces at play. Some theories propose sterile neutrinos, even more elusive variants that might interact only via gravity, potentially weaving the fabric of dark matter itself. Others suggest neutrinos could be Majorana particles, acting as their own antimatter counterparts, which might explain why matter dominates the cosmos. Every time a neutrino detector catches a flicker of light from one of these phantoms, we're not just studying particles, we're decoding a hidden layer of reality, one that governs everything from the birth of galaxies to the fate of collapsing stars. And as we peel back these secrets, we're uncovering a universe far stranger, more dynamic, and more interconnected than we ever imagined, all written in the silent dance of the universe's most elusive messengers. Somewhere beyond the stars we can see, beyond even the farthest reaches of our cosmic maps, something colossal is pulling us toward it at 22 million miles per hour. This is the Great Attractor, a gravitational anomaly so powerful it's dragging entire galaxies, including our Milky Way, through the void like leaves caught in a river's current. For decades, astronomers scratched their heads over this mystery. Why were thousands of galaxies all streaming toward a single point in space, toward a region so obscured by the Milky Way's own dust and stars that it's like staring into a cosmic blind spot? The first clues emerged in the 1970s when scientists noticed something odd about the motion of nearby galaxies. Instead of evenly dispersing with the universe's expansion, they were all veering toward a specific patch of sky near the constellation Centaurus. Calculations suggested an incomprehensible mass equivalent to tens of thousands of Milky Ways was lurking there, warping spacetime with its gravity. But when telescopes turned in that direction, they saw almost nothing, just a hazy wall of interstellar dust blocking our view, as if the universe itself were hiding something. What lies behind that curtain? The leading theory points to the Norma cluster, a dense gathering of galaxies about 250 million light-years away, surrounded by even larger structures like the Shapley supercluster. These titanic assemblies of matter could generate enough gravitational pull to explain part of the anomaly. But here's the catch: even combined, they don't account for all the force we're experiencing. That discrepancy has fueled wilder speculation. Could there be an unseen concentration of dark matter so vast it defies our models? Or something more exotic, like a cosmic defect in space-time left over from the universe's birth? Peering through the Milky Way's obstructions required clever workarounds. Astronomers turned to X-ray and radio telescopes, which can pierce the dust, revealing hints of massive galaxy clusters normally invisible to optical instruments. Meanwhile, new surveys like the Dark Energy Telescope are mapping the motions of galaxies in unprecedented detail, tracing the gravitational currents that might lead us to the Great Attractor's heart. What's truly humbling is the scale of our predicament. This unseen force isn't just tugging on our galaxy, it's part of an even larger flow, dragging us toward an incomprehensibly vast structure called the Laniakea supercluster, of which the Great Attractor may be just one gravitational node. It's like realizing the river you're floating down is actually a tiny tributary of the Amazon. The deeper we probe, the clearer it becomes. The Great Attractor isn't just a curiosity. It's a reminder of how much of the universe's architecture remains hidden in plain sight, warping reality from the shadows. And as we slowly peel back the layers of dust and distance, we're not just solving a cosmic mystery, we're uncovering the invisible hands that have been shaping our galactic journey for billions of years. In the vast silence between galaxies, where darkness stretches for millions of light-years, cosmic fireworks occasionally erupt, blinding flashes of radio energy so powerful they outshine entire galaxies for a fraction of a second. These are fast radio bursts, some of the most enigmatic signals ever detected. First discovered in 2007, these bursts pack more energy than the Sun emits in 80 years into mere milliseconds, vanishing before astronomers can pinpoint their origins. What's baffling isn't just their intensity, it's that they seem to come from nowhere, echoing across the cosmos like a fingerprint with no hand attached. The leading suspect, magnetars neutron stars with magnetic fields so strong they could strip the information from a credit card halfway across the solar system. When these hypercharged stars experience starquakes or magnetic eruptions, they might unleash bursts of energy detectable across the universe. In 2020, astronomers caught a smoking gun. A magnetar in our own galaxy emitted a radio burst eerily similar to those from deep space. But here's the catch: most fast radio bursts don't match this profile. Their signals are cleaner, brighter, and often repeat unpredictably. unlike anything we've seen from known magnetars. That inconsistency has fueled wilder theories. Could colliding neutron stars or evaporating primordial black holes be the culprits? Some pulses arrive with a telltale dispersion, a smearing of wavelengths suggesting they've traveled through dense plasma, possibly from the halos of distant galaxies. Others repeat in patterns so strange they've sparked speculation about artificial origins. While extraterrestrial civilizations remain a fringe hypothesis, the sheer variety of bursts suggests we might be dealing with multiple cosmic phenomena, each more bizarre than the last. What makes these bursts more than just a curiosity is their potential as cosmic tools. As they traverse the universe, their radio waves interact with the sparse electrons between galaxies, allowing scientists to measure the universe's hidden matter. It's like using lightning to illuminate a foggy landscape. Each burst maps the invisible web of gas and plasma we'd never see otherwise. New telescopes like Canada's CHIME and Australia's ASCAP are now catching dozens of these events monthly, building a catalogue that could revolutionize our understanding of cosmic structure. Yet with every answered question, new mysteries emerge. Some bursts arrive with polarization twists, hinting at extreme magnetic environments. Others repeat on cycles lasting months, suggesting orbital mechanics at play. The universe seems to be teasing us with these cryptic signals, each one a piece of a puzzle we're only beginning to assemble. Whether they're the death cries of exotic stars or something even stranger, fast radio bursts remind us that the cosmos still holds secrets waiting to be decoded, and that some of its loudest voices come from the darkest voids. The cosmic microwave background, the faint afterglow of the Big Bang, should be the ultimate cosmic fingerprint, a random splatter of hot and cold spots revealing the universe's infancy. But when scientists mapped it in detail, they stumbled upon something unsettling. The largest fluctuations in temperature aren't scattered chaotically. They're subtly aligned along a mysterious axis, as if the universe itself has a hidden compass needle pointing toward the constellations Leo and Aquarius. This eerie pattern, nicknamed the axis of evil, shouldn't exist according to standard cosmology, and its discovery has split physicists into warring camps. Is it a statistical fluke, a sign of unknown physics, or could it be evidence that our universe isn't as random as we thought? At the heart of the controversy is the cosmological principle, the bedrock assumption that the universe looks roughly the same in all directions on large scales. The axis of evil challenges this directly. Imagine tossing confetti in the air and watching every piece land pointing northeast. That's the level of weirdness we're dealing with. Some researchers argue it's just an illusion, a trick of how we process cosmic microwave background data. Others propose more radical explanations. Perhaps the universe was stretched unevenly during inflation, creating a preferred direction. Or maybe what we're seeing is the gravitational imprint of a neighboring universe brushing against ours in the multiverse, leaving a cosmic thumbprint on the sky. The most mind-bending possibility, the alignment might be a relic from before the Big Bang. Certain quantum gravity theories suggest spacetime could have had structure even at the moment of creation, like wrinkles in a sheet that persist no matter how much you stretch it. If true, the axis of evil could be a fossil from a time before time, a whisper from the universe's absolute beginning. That would mean our observable cosmos isn't perfectly uniform after all, but carries traces of its birth conditions in its very geometry. Critics aren't convinced. They point out that the alignment's statistical significance wobbles depending on how you analyze the data. Newer measurements from the Planck satellite show the effect is weaker than initially thought, though still puzzling. Meanwhile, alternative theories are gaining traction, like the idea that dark energy flows differently along this axis, subtly warping the cosmic microwave background over billions of years. What's undeniable is how this debate exposes the limits of our knowledge. The axis of evil reminds us that the universe might still be hiding its rulebook, and that the deeper we look, the more we find patterns we can't yet explain. Whether it's a flaw in our models or a crack in reality itself, this cosmic enigma proves one thing: the universe is far stranger, far more intricate, and far more mysterious than we ever imagined. Imagine every decision you've ever made, every path taken or ignored, exists simultaneously in alternate realities where different versions of you live out those unchosen possibilities. This isn't just science fiction. It's one interpretation of the multiverse, a staggering idea born from the equations of cosmic inflation. According to this theory, our universe might be just one bubble in an endless froth of universes, each with its own unique laws of physics, constants, and even dimensions. The concept emerges naturally from inflation's math. When space-time underwent that explosive expansion at the universe's birth, quantum fluctuations could have caused some regions to stop inflating earlier than others, forming isolated pocket universes like bubbles in boiling water. These pockets would then evolve independently with wildly different physical properties. In some, gravity might be stronger, preventing stars from forming. In others, electromagnetism could dominate, creating bizarre chemistry. Our universe's delicate balance, where constants like the strength of gravity or the mass of electrons allow for galaxies, planets, and life, might not be a miracle. It could just be statistical inevitability in an infinite ensemble where every possible configuration exists somewhere. Critics argue this makes the multiverse untestable, a philosophical notion rather than science. But physicists are hunting for clues. One approach examines the cosmic microwave background for bruises left by collisions with other bubble universes in our distant past. Another looks for anomalies in the distribution of galaxies that might betray gravitational tugs from neighboring universes. Then there's string theory's landscape, which suggests there could be 10 to the power of 500 possible vacuum states, each representing a unique universe with its own physics. The implications are profound. If true, the multiverse could explain why our universe seems improbably fine-tuned for life without invoking a designer. It also raises existential questions. Are there versions of reality where dinosaurs never went extinct, where civilizations mastered interstellar travel? Or where the very concept of time is unrecognizable? The multiverse doesn't just expand space, it explodes the imagination, challenging us to rethink what reality even means. Yet for all its grandeur, the idea remains contentious. Some scientists propose alternatives, like an evolving universe where constants slowly change over cosmic time. Others suggest we're misreading the data entirely. But whether the multiverse is proven or not, its mere possibility reshapes our cosmic perspective, reminding us that the strangest truths might still lie beyond the horizon of our observable universe, and that our reality could be just one verse in an endless cosmic poem. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing trillions of stars. Given those staggering numbers, the math suggests intelligent life should be everywhere, so why does the cosmos feel so silent? This eerie contradiction is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If life is common, we should see evidence of advanced civilizations. Yet after decades of searching, from radio telescopes scanning for signals to probes scouring Mars for microbes, we've found nothing but empty space. This cosmic silence isn't just puzzling, it's unsettling. One chilling explanation is the Great Filter hypothesis, a theoretical barrier that prevents life from progressing to interstellar expansion. The filter could lie in our past, meaning the emergence of life or intelligence is astronomically rare. Maybe DNA forming or cells evolving was a freak accident, leaving us alone in the void. But the darker possibility, the filter is ahead of us. Perhaps all civilizations hit a self-destructive wall, nuclear war, runaway AI, or ecological collapse that we haven't faced yet. The absence of aliens wouldn't be a mystery, it'd be a warning. Other theories paint less apocalyptic scenarios. Advanced civilizations might build Dyson spheres, megastructures enveloping stars to harvest their energy, rendering them invisible to our telescopes. Or they could communicate via neutrinos or quantum entanglement, technologies we're too primitive to detect. Some scientists suggest we're like ants in a rainforest, unaware of the conversations happening above us in frequencies and scales beyond our perception. Then there's the zoo hypothesis, that aliens know we're here but deliberately avoid contact, observing us like a cosmic nature preserve. Or the idea that spacefaring cultures transcend physical forms, uploading their consciousness into virtual realities with no need to explore the stars. Even our definition of life might be too narrow. What if intelligence exists as floating plasma in gas giants or as sentient networks within nebulas? The paradox forces us to confront profound questions. Are we the universe's firstborn, destined to spread life through the cosmos? Or are we precariously balanced between a miraculous past and a perilous future? With new telescopes like the James Webb scanning exoplanet atmospheres for biosignatures and projects like SETI expanding their search, we might be on the verge of answers. But until then, the silence remains a cosmic riddle whispering that either we're impossibly special or we're missing something fundamental about the nature of existence itself. One summer night in 1977, a radio telescope in Ohio picked up something extraordinary, a signal so unusual that the astronomer who discovered it scrawled, "Wow." In red ink on the printout, for 72 seconds, the Big Ear telescope detected a narrowband radio burst 30 times stronger than the background noise, perfectly matching the expected signature of an artificial extraterrestrial transmission. It came from the direction of the constellation Sagittarius, lasted exactly the duration the telescope could monitor that patch of sky, and then vanished without a trace. Decades of follow-up searches have turned up nothing, leaving the wow signal as one of science's most tantalizing maybes, a fleeting whisper from the cosmos that refuses to be explained. What makes this signal so perplexing is its specificity. Natural cosmic radio sources like pulsars or quasars emit broad-spectrum noise, but the wow signal was laser-focused at 1420 MHz, the frequency of hydrogen, the universe's most abundant element. Scientists have long theorized that advanced civilizations might use this universal channel to broadcast their presence, much like sailors using specific distress frequencies. The signal also displayed a telltale intensity curve, rising and falling exactly as expected for a fixed source passing through the telescope's field of view. Every characteristic pointed to something artificial, yet no human-made satellite or aircraft matched its profile. Theories range from the mundane to the extraordinary. Some suggest it was a reflected transmission from Earth, perhaps a military experiment or a rogue satellite, but no records match the timing or frequency. Others propose a natural but unknown astrophysical phenomenon, like a comet's hydrogen cloud emitting radio waves, yet follow-up observations of comets in the area came up empty. Then there's the electrifying possibility, an alien beacon intentionally or accidentally aimed our way. If so, it might have been a one-time event, a dying civilization's final shout into the void, or a targeting blip from a passing probe. Efforts to solve the mystery continue. The Breakthrough Listen project recently scanned the same region using modern equipment, hoping to catch a repeat. Meanwhile, new analysis techniques applied to old data suggest the signal might have originated around a sun-like star 2,000 light-years away. But until another signal arrives or we uncover some overlooked terrestrial explanation, the wow remains suspended between proof and possibility, a cosmic Rorschach test inviting us to wonder, was it a glitch, a fluke, or the moment humanity first heard the universe whisper back? Out beyond Neptune's frosty orbit, where sunlight weakens to a dim glimmer, thousands of icy bodies drift in the Kuiper belt, our solar system's final frontier. Astronomers expected this region to gradually thin out as they mapped more distant objects, but instead they hit a wall. At roughly 50 astronomical units from the Sun, about 7.5 billion kilometers, the population of Kuiper belt objects doesn't just dwindle. It plunges off a cliff, dropping to near zero as if someone drew a cosmic boundary line. This sudden cutoff, known as the Kuiper cliff, defies every model of how planetary systems form, and the best explanations scientists have come up with sound like something from a space opera. One leading theory points to an unseen ninth planet, a massive world lurking in the darkness, its gravity herding smaller objects into tight clusters while clearing out others. Calculations suggest this hypothetical planet could be 5 to 10 times Earth's mass, orbiting so far out that it takes 10,000 to 20,000 years to complete a single trip around the Sun. If confirmed, it would rewrite our solar system's map, revealing that even after centuries of observation, we've missed a neighbor big enough to perturb the orbits of everything beyond Neptune. But here's the catch: despite exhaustive searches, no one's found it yet. The very emptiness at the Kuiper cliff might be its calling card, a ghostly signature etched into the void. There's another possibility, even more dramatic. About 4.5 billion years ago, when our solar system was in its chaotic infancy, a passing star might have strayed dangerously close. This interstellar intruder could have yanked countless Kuiper belt objects away, flinging them into deep space or stealing them outright, leaving behind only the cliff we see today. It's a cosmic robbery scenario, with the thief long gone and the evidence frozen in the unusual orbits of surviving objects like Sedna, which loops far beyond the expected edge of the Kuiper belt on a path that hints at ancient disruption. Yet some researchers argue we're overcomplicating things. They suggest the cliff could simply mark where the primordial disk of material that formed our solar system originally ended, a fossilized edge from a time when the Sun's birth cloud ran out of building blocks. Others propose that over billions of years, subtle gravitational tugs from Neptune or collisions between objects ground the outermost debris into dust too fine to detect. But these theories struggle to explain why the drop-off is so abrupt, as if someone flipped a switch. The mystery isn't just academic. Understanding the Kuiper cliff could reveal hidden chapters of our solar system's history, whether it's the gravitational fingerprint of a distant giant planet, the scars of a stellar close call, or something even stranger. Every new survey of the outer solar system, from ground-based telescopes to missions like New Horizons, brings us closer to an answer, and when we find it, we won't just solve a puzzle about icy rocks in the dark. We'll uncover forces that shaped our cosmic neighborhood in ways we're only beginning to imagine. On October 19, 2017, astronomers spotted something unprecedented streaking through our solar system at nearly 200,000 miles per hour, an object so strange that its discovery would ignite one of the fiercest debates in modern astronomy. Named Oumuamua Hawaiian for scout, this dark reddish visitor wasn't just another comet or asteroid. Its trajectory revealed an impossible truth. It came from another star system, making it the first known interstellar traveler ever detected. But what made Oumuamua truly baffling wasn't where it came from, it was how it behaved. Unlike typical comets that shed gas and dust when warmed by the sun, Oumuamua showed no visible tail. Yet it accelerated as it departed, as if pushed by some unseen force. Its shape, inferred from brightness variations, resembled a bizarre cigar roughly 800 meters long but only 80 meters wide, 10 times more elongated than any known natural space rock. Most startling of all, its reflectivity. Oumuamua was at least 10 times shinier than typical cometary surfaces, gleaming like polished metal as it tumbled through space. The scientific community scrambled for explanations. One camp argued it was an exotic type of comet, with hidden ices that vaporized unevenly to produce thrust. Others proposed it might be a fragment of a shattered planet, sheared off during some ancient cosmic collision and sent careening between stars. But Harvard astronomer Avi Loeb offered a more provocative idea. What if Oumuamua wasn't natural at all? Its unusual acceleration, he noted, matched what you'd expect from a light sail, a thin, reflective structure pushed by starlight like a boat's sail catching wind. Could this be discarded technology from an alien civilization, drifting through the galaxy like interstellar debris? Skeptics pushed back hard. Natural explanations, they argued, were far more likely. Some suggested Oumuamua might be a hydrogen iceberg, a theoretical object that could explain both the acceleration and lack of visible outgassing. Others pointed to observations showing it didn't change speed as smoothly as an artificial probe should. The debate grew so heated it spilled beyond academic journals into mainstream headlines, with critics accusing Loeb of sensationalism, while he countered that science should never dismiss possibilities without evidence. What makes Oumuamua's mystery endure isn't just the unanswered questions, it's what the object represents. For centuries, we've wondered if we're alone in the cosmos. Now we have proof that interstellar objects can reach us, and that some defy easy classification. Future telescopes like the Vera Rubin Observatory will scan for more visitors, potentially catching them earlier for detailed study. Until then, Oumuamua remains a cosmic Rorschach test, a silent, speeding enigma that challenges us to confront how readily we project our hopes and fears onto the unknown. Whether natural or artificial, its greatest lesson might be this: the universe is far stranger than our textbooks suggest, and the next odd visitor could rewrite the rules at any moment. In the vast emptiness between planets, where gravity's grip weakens and spacecraft glide with near-perfect predictability, something strange happened to NASA's Pioneer probes. These trailblazing missions, launched in the 1970s to explore the outer solar system, began drifting off course not by much, but enough to baffle physicists for decades. As they ventured beyond Jupiter and Saturn, both Pioneer 10 and 11 experienced an unexplained deceleration, as if some unseen hand was gently tugging them backward. The effect was tiny, less than a billionth of a gravity's pull on Earth, but in the pristine physics lab of deep space, even the slightest anomaly can upend our understanding of the cosmos. At first, scientists scrambled to explain the discrepancy. Could it be gravitational tugs from undiscovered Kuiper belt objects, leaking fuel altering their trajectories? Or was this the first hint of a flaw in Einstein's theory of general relativity? The most tantalizing possibility was that the probes had stumbled upon a previously unknown force, a whisper of new physics lurking in the darkness. Some theorists even proposed modifications to gravity itself, suggesting that on cosmic scales, the laws we take for granted might behave differently. Then came the smoking gun, or so it seemed. After years of painstaking analysis, engineers realized the probe's own heat could explain the anomaly. As the Pioneer's radioactive power sources decayed, they emitted infrared radiation unevenly, with slightly more warmth escaping from the backs of the spacecraft than the fronts. This tiny imbalance acted like a faint but constant push, slowing the probes just enough to match the observed drift. Case closed, or was it? Skeptics pointed out lingering inconsistencies. The thermal model didn't perfectly account for the magnitude of the deceleration, and other spacecraft traveling similar distances, like New Horizons, haven't shown the same effect. Could there still be an undiscovered factor at play? The debate reveals how even the smallest mysteries in space can lead us to question our deepest assumptions. What makes the Pioneer Anomaly so compelling isn't just the technical puzzle, it's the reminder that our understanding of the universe is always provisional. Every unexplained flicker in the data, every tiny deviation from expectation, could be the thread that unravels an even grander truth. And as future probes venture farther into the unknown, they might yet encounter forces we can't explain, forces that, like the pioneers before them, nudge us toward the next great leap in cosmic understanding. High above our planet, hidden in the swirling chaos of Earth's orbital traffic, an object whispers through the darkness, one that conspiracy theorists insist isn't human-made at all. They call it the Black Knight satellite, a supposed alien artifact that's been circling Earth for 13,000 years, silently watching our civilization rise and fall. The legend claims this mysterious spacecraft was first detected by Nikola Tesla in 1899 through strange radio signals, then spotted again by military radar in the 1950s, tracking unidentified objects in polar orbit, a trajectory no human satellite used at the time. But here's where fact and fiction collide like two satellites in the night. Astronomers have a far simpler explanation: space junk. The most likely culprit is a thermal blanket lost during a 1965 spacewalk from the Gemini 4 mission, later photographed during a 1998 space shuttle flight. That particular debris fragment matched the descriptions of the so-called Black Knight, a tumbling, irregular shape reflecting sunlight in unpredictable flashes. Even the ancient signals Tesla picked up align with known pulsars, celestial lighthouses that emit regular radio bursts. Yet despite these rational explanations, the myth endures, fueled by grainy NASA photographs and a persistent human desire to believe we're not alone in the cosmos. What makes the Black Knight legend so enduring isn't just the mystery, it's how perfectly it mirrors our technological anxieties. In the 1950s, at the height of Cold War paranoia, the idea of an alien observer watching our nuclear tests fit the era's fears. Today, in an age of satellite surveillance and AI, the tale evolves. Now it's a dormant alien probe waiting to activate, or a warning beacon placed by ancient visitors. Pop culture latched onto these themes, from Marvel Comics adaptation to conspiracy documentaries framing government denials as proof of a cover-up. Modern tracking data reveals the sobering truth. Every alleged Black Knight sighting correlates with known debris, discarded rocket parts, defunct satellites, even a lost glove from astronaut Ed White's historic spacewalk. The International Space Station's cameras constantly capture such debris tumbling through orbit, their twisted metal forms occasionally catching the light in ways that spark wild speculation. Yet the human imagination keeps reaching, transforming mundane space trash into something extraordinary, because sometimes the universe feels more exciting when it might still hold ancient secrets just beyond our grasp. Perhaps the real lesson of the Black Knight isn't about aliens at all, but about how we see ourselves in the vastness of space. When we look up, we don't just see cold equations and floating metal. We see stories, possibilities, and the lingering hope that someone or something might be looking back. And in that sense, the legend lives on, not in orbit, but right here on Earth, where our oldest questions about the cosmos still outshine even the brightest satellite. The moon hangs in our sky as a silent, airless world, a place where compasses should spin uselessly without a magnetic field to guide them. Yet ancient lunar rocks tell a different story. Locked within their crystalline structures are traces of a long-lost magnetic field, one that once rivaled Earth's in strength. Here's the puzzle. The moon's core is far too small and cold to have generated such a powerful dynamo the way Earth does. So how did our closest cosmic neighbor, a world just 1% of our planet's mass, briefly cloak itself in a magnetic shield strong enough to deflect solar storms? For decades, this contradiction baffled scientists. Traditional dynamo theory, where a molten, electrically conductive core churns like a planetary-scale generator, couldn't explain the moon's magnetic history. Its core simply didn't have the fuel for such an engine, but recent computer simulations have unveiled two tantalizing possibilities, both tied to the moon's violent youth. The first revolves around colossal impacts. 4 billion years ago, the inner solar system was a shooting gallery, with asteroids the size of cities regularly slamming into the moon. These collisions didn't just carve craters, they might have supercharged the moon's interior. Imagine a gargantuan impactor striking the surface with enough force to send seismic waves ricocheting through the mantle, stirring the core like a spoon in molten metal. This sudden, chaotic motion could have jump-started a temporary dynamo, with the magnetic field fading as the turmoil settled. The second theory points to an even subtler force, tidal friction. Early in its history, the moon orbited much closer to Earth, and our planet's gravity stretched and squeezed its interior like putty. This constant flexing generated heat through friction, enough, perhaps, to keep parts of the core molten and convective. Just as Earth's dynamo relies on the movement of liquid iron, the moon's might have been powered by this cosmic tug of war, its magnetic field pulsing in rhythm with its changing orbit. As the moon gradually drifted outward, the tidal forces weakened and the dynamo sputtered out. What's astonishing is how these theories transform our understanding of planetary magnetism. We once thought only large, geologically active worlds could sustain magnetic fields, but the moon's history suggests even small, seemingly inert bodies can briefly tap into extraordinary forces, whether through catastrophic collisions or the delicate dance of orbital mechanics. Future missions could settle the debate. By analyzing lunar rocks from different eras, scientists hope to map the field's rise and fall, matching its timeline to periods of intense bombardment or tidal heating. The implications stretch far beyond our moon. If impacts or tides can forge magnetic shields, then countless exomoons orbiting distant gas giants might have once harbored similar protections, shielding hypothetical alien life from deadly cosmic rays. The moon's magnetic mystery isn't just a curious footnote in planetary science. It's a reminder that even the quietest worlds can have tumultuous pasts, and that the universe often hides its most extraordinary secrets in the unlikeliest places. In the constellation Cygnus, a star named KIC 846285-2, better known as Tabby's star, flickers like a cosmic candle in the wind. Unlike ordinary stars, which dim and brighten in predictable rhythms, this one behaves like nothing astronomers have ever seen. Its light doesn't just dip by fractions of a percent, it plummets by up to 22% at irregular intervals, as if something colossal is passing in front of it. The dips are too dramatic and chaotic to be explained by planets. Even a Jupiter-sized world would block only 1% of the star's glow. So what's casting these immense shadows across the face of Tabby's star? The answer could rewrite our understanding of cosmic phenomena, or just maybe hint at intelligence beyond Earth. At first, scientists assumed the culprit was simple, a swarm of comets or a thick disk of dust orbiting the star. These could fragment light unevenly, creating the erratic dimming patterns we observe. But when researchers calculated the dust requirements, the numbers didn't add up. To block that much light so sporadically, Tabby's star would need a cloud of debris far denser than anything found around similar stars, enough to make our own asteroid belt look like a scattering of pebbles. Even stranger, long-term observations revealed the star is gradually fading over decades, as if something is steadily accumulating between us and its light. This is where the speculation takes a leap. In 2015, astronomer Jason Wright proposed a radical idea. What if the dimming isn't natural at all? Advanced civilizations, he suggested, might build megastructures like Dyson swarms, vast arrays of solar collectors encircling a star to harvest its energy. Such constructs wouldn't be solid shells but sprawling networks of orbiting panels, which could cause irregular dips as they pass in front of the star from our vantage point. The concept isn't pure science fiction. Physicist Freeman Dyson first theorized about these structures in the 1960s as a potential signature of highly developed alien societies. Skeptics, of course, have counterarguments. Recent spectral analysis shows the dimming affects shorter wavelengths more than longer ones, a telltale sign of fine dust, not solid objects. Dust scatters blue light more efficiently than red, just as Earth's atmosphere makes our sky appear blue. This finding tilts the scales back toward natural explanations, like a shattered planet or a colossal collision leaving behind drifting debris. Still, the dust itself raises questions. Why is it so unevenly distributed? And what event could have produced such an enormous, chaotic cloud in the first place? The mystery deepens when you consider Tabby's star isn't alone. Astronomers have since identified dozens of other Dipper stars with similar, though less extreme, behavior. Some exhibit symmetrical dips, suggesting rings or spiral structures. Others show signs of icy material evaporating near their surfaces. This growing catalogue implies Tabby's star might be the most dramatic example of a broader cosmic phenomenon, one we're only beginning to recognize. So where does that leave us? The most plausible answer is still dust, but dust of an unusual kind, shaped by processes we don't yet fully understand. Yet the mere fact that scientists seriously entertain the megastructure hypothesis, even briefly, speaks volumes. Tabby's star forces us to confront how little we know about the universe's potential for complexity. Whether the culprit is drifting debris or something far more extraordinary, this flickering enigma reminds us that the cosmos still holds puzzles capable of stretching our imaginations to the breaking point. And as we watch and wait for more data, one thing is certain: Tabby's star isn't done surprising us yet. Galaxies should be held together by dark matter, that invisible cosmic glue making up most of the universe's mass. But in 2018, astronomers stumbled upon something that shouldn't exist: NGC 1052 DF2, a ghostly galaxy drifting through space with almost none of this mysterious substance. This cosmic oddball isn't just unusual, it defies everything we thought we knew about how galaxies form and survive. At first glance, NGC 1052 DF2 looks like any other diffuse galaxy, a faint, wispy collection of stars so spread out you could almost see straight through it. But when researchers measured the motions of its star clusters, they found something shocking. The stars were moving far slower than expected, suggesting the galaxy had barely any mass at all. Without dark matter's gravitational pull, NGC 1052 DF2 should have torn itself apart long ago. Yet here it is, floating calmly in the cosmic sea, as if the rules of physics don't apply. The discovery sent shockwaves through astrophysics. If dark matter is the universe's scaffolding, how did this galaxy build itself without it? One possibility is that NGC 1052 DF2 is a tidal dwarf, a galaxy born from debris ripped away during a violent collision between larger galaxies. Unlike normal galaxies, which form in halos of dark matter, tidal dwarfs inherit mostly ordinary matter from their parent galaxies, but even this explanation doesn't quite fit. NGC 1052 DF2 is too isolated, too pristine, with no signs of the chaotic origins typical of tidal remnants. Then there's the radical alternative. Maybe dark matter isn't the only way to explain gravity's grip. Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently at cosmic scales, eliminating the need for dark matter entirely. For decades, mainstream cosmology dismissed MUND as fringe science, but galaxies like NGC 1052 DF2 give it unexpected credibility. If gravity truly works as MUND predicts, then this galaxy's serene existence suddenly makes sense. Of course, skeptics aren't ready to abandon dark matter just yet. Some argue that NGC 1052 DF2 might have been stripped of its dark matter by a close encounter with a massive neighbor, though no culprit galaxy has been found. Others suggest measurement errors. Perhaps the star clusters we're tracking aren't actually part of the galaxy, skewing the results, but follow-up studies have only deepened the mystery. More dark matter deficient galaxies have since been discovered, including one with so little mass that its stars move slower than snails crawl. What's at stake here isn't just one galaxy's strange behavior. If NGC 1052 DF2 isn't a fluke, it could mean our understanding of gravity is incomplete, or that dark matter is far more complex than a single universal particle. Perhaps it clumps unevenly, leaving voids where galaxies like this can form against all odds. Or maybe, just maybe, the universe is subtly rewriting the rules in places we've only begun to explore. Either way, this faint smudge of stars is forcing us to confront a humbling truth. When it comes to the cosmos, even our best theories are just sketches waiting to be redrawn. Deep in the constellation Boötes, astronomers have found a cosmic paradox, a spherical region of space so empty it defies logic. Spanning 330 million light-years, the Boötes void is a staggering expanse of nothingness, a desert so vast you could fit 20,000 Milky Ways inside with room to spare. Most voids between galaxies measure 50 to 100 million light-years across, but this one dwarfs them all. If you stood at its center, you'd see almost no galaxies in any direction, just an eerie, starless blackness stretching farther than the mind can comprehend. How does such a void exist? The standard model of cosmic structure formation predicts that matter should clump together unevenly, leaving some regions emptier than others, but nothing on this scale. Imagine stirring cream into coffee and finding, instead of swirls, a single bubble the size of the cup. The Boötes void shouldn't be possible unless our understanding of the universe's large-scale structure is missing something fundamental. Some theorists speculate that smaller voids merged over time, like soap bubbles coalescing into one giant cavity. Others propose more exotic explanations, like quantum fluctuations in the early universe that created defects in space-time cosmic scars where matter never condensed. Then there's the chilling possibility that the void isn't empty at all. What if it's filled with dark energy, the same mysterious force accelerating the universe's expansion? In such a region, dark energy's repulsive gravity could have pushed matter away like an invisible broom, leaving behind a barren expanse. Alternatively, the void might house primordial black holes or other invisible entities that cleared the area without leaving a trace. The few galaxies that do cling to the void's edges only deepen the mystery. These isolated survivors, like lonely outposts on the frontier, exhibit strange properties. Some are red and dead galaxies that aged prematurely, their star formation snuffed out by the void's harsh environment. Others show signs of extreme tidal forces, as if the void itself is stretching them apart. Studying these galaxies is like examining artifacts from a shipwreck, offering clues about the forces that shape this cosmic anomaly. What's truly humbling is the scale of our uncertainty. The Boötes void reminds us that even in an era of cosmic surveys and supercomputer simulations, the universe can still produce structures that leave us utterly baffled. Whether it's a flaw in our models, a quirk of dark energy, or something even stranger, this colossal emptiness challenges us to rethink how the cosmos organizes itself, and what other unimaginable structures might lurk in the darkness beyond our maps. In the cosmic microwave background, the faint afterglow of the Big Bang, there's a patch of sky that doesn't belong, stretching across hundreds of millions of light years. This region glows slightly colder than its surroundings, as if someone pressed an ice pack against the infant universe. Astronomers call it the cold spot, and it's one of the most tantalizing anomalies in modern cosmology. The temperature difference is subtle, just a few millionths of a degree, but in a universe that's supposed to be uniform on large scales, even tiny deviations can signal something extraordinary. What makes the cold spot so perplexing isn't just its temperature, it's the sheer size. Random fluctuations in the cosmic microwave background are common, but statistical analysis shows the odds of one this large forming by chance are less than 1 in 50. That's raised wild speculation. Could this be a scar from a collision with another universe? Some theories of the multiverse suggest that our cosmos is just one bubble in an infinite froth of universes, each with its own physical laws. If one of these bubbles brushed against ours during inflation, the energy released might have left a mark, a cosmic bruise frozen in time. Skeptics aren't convinced. They point to more mundane explanations, like a vast supervoid, an enormous, underdense region of space where fewer galaxies mean less gravitational pull, subtly cooling light passing through it. Yet even this theory has problems. Surveys of galaxy distributions suggest the required void would need to be improbably large, far beyond what standard models predict. Others propose exotic physics, like a flaw in the fabric of spacetime itself, a cosmic knot left over from the universe's birth. The debate isn't just academic. If the cold spot truly is evidence of a multiverse, it would revolutionize our understanding of reality, proving we're part of something far grander than a single, isolated cosmos. Future telescopes, like the European Space Agency's Euclid mission, could settle the argument by mapping the distribution of galaxies and dark matter in unprecedented detail. Either way, this chilly anomaly reminds us that the universe still holds mysteries capable of shaking the foundations of physics, and that sometimes the coldest corners of space might hide the hottest clues. Somewhere in the constellation Serpens, a world unlike any other spins in silent darkness, a planet so dense that a single sugar cube-sized chunk would weigh more than a car. Known as PSR J 1719-1438b, this bizarre orb isn't just another rocky exoplanet. It's a cosmic diamond, a crystallized behemoth forged from crushed carbon, orbiting the corpse of a dead star at breakneck speed. The story begins with its parent star, or rather, what's left of it. The planet circles a pulsar, the rapidly spinning remnant of a supernova explosion that beams radiation like a lighthouse from hell. Pulsar planets are already rare, fewer than a dozen are known, but this one stands apart. When astronomers first detected subtle wobbles in the pulsar's radio pulses in 2011, they realized something massive was tugging on it. The culprit, a planet roughly 5 times Earth's mass, squeezed into a ball smaller than Jupiter. here's where the mystery deepens. A planet that dense can't be made of ordinary rock or gas. The math points to something extraordinary: crystallized carbon, the same atomic structure that gives diamonds their brilliance, but compressed under pressures so intense it defies imagination. Picture the carbon in a pencil's graphite core, but subjected to gravity 1,000,000 times stronger than Earth's, rearranged into a lattice of perfect crystals stretching across an entire world. How does such a planet form? Traditional models fail to explain it. Normally, planets coalesce from dusty disks around young stars, but pulsars are anything but normal. One theory suggests this diamond world was once a white dwarf, a dying star's dense core that lost nearly all its outer layers to the pulsar's gravity, leaving behind a carbon-rich skeleton. Another proposes it's the shattered remains of a gas giant, its lighter elements stripped away by the pulsar's fierce radiation, leaving only a glittering core. The implications are staggering. If planets like this exist, they hint at formation processes we've never witnessed: cosmic alchemy transforming stars into gemstones. They also raise tantalizing questions. Could there be layers of liquid carbon beneath the crystalline surface? Might the pressures create exotic forms of matter we've never seen? And if diamonds are forever, what does that mean for a world that's essentially eternal? Yet for all its allure, PSRJ 1719-1438b is no glittering paradise. Bathed in lethal radiation from its pulsar, shrouded in perpetual night, it's a monument to extremes, a reminder that the universe's most dazzling wonders are often its most inhospitable. As we uncover more of these cosmic diamonds, they're not just rewriting planetary science, they're proving that reality, when pushed to its limits, can outshine even our wildest fantasies. When the James Webb Space Telescope peeled back the cosmic curtain to reveal the universe's first galaxies, astronomers expected to see infant structures, clumsy, unformed collections of stars just beginning to coalesce from the primordial darkness. Instead, JWST found cosmic toddlers bench-pressing weights meant for grown adults. These ancient galaxies, spotted as they were just 300 to 400 million years after the Big Bang, shouldn't exist by our current models. They're too massive, too polished, too finished. One in particular, dubbed Glass Z13, weighs in at over 1 billion suns, a cosmic heavyweight at a time when the universe was barely 2% of its current age. The problem isn't just their size, it's their sophistication. These galaxies are already rotating disks with distinct structures, some even showing evidence of multiple stellar generations. That's like finding a perfectly baked loaf of bread in an oven that's only been on for 30 seconds. Standard cosmology dictates that galaxies grow gradually, with tiny fluctuations in the early universe's density slowly collapsing under gravity over billions of years. Yet here we're seeing fully fledged giants appearing almost instantly, as if the universe hit fast forward. So where did our models go wrong? One possibility is that dark matter, the invisible scaffolding of the cosmos, behaves differently in the early universe than we assumed. Maybe it clumped together faster, creating dense pockets that accelerated star formation. Alternatively, the first stars might have formed far more efficiently than we thought, converting nearly all available gas into suns in a single, furious burst. Some theorists even speculate about exotic early energy sources, like primordial black holes or decaying dark matter particles that could have jump-started galaxy growth. Then there's the radical alternative. What if the universe itself is older than we think? If the Big Bang wasn't the absolute beginning but a transition from some prior state, a bounce from a previous contraction, these galaxies might have had a head start. Others suggest the speed of light or the strength of gravity could have varied in the early cosmos, rewriting the rules of cosmic assembly. But before we tear up the textbooks, skeptics urge caution. JWST observations rely on redshift measurements to estimate distance and age, and cosmic dust or unusual stellar compositions might be skewing the data. Some of these galaxies could also be rare outliers, cosmic lottery winners that formed under freakishly ideal conditions. Upcoming spectroscopic studies will dissect their light for definitive answers. What's undeniable is the thrill of the challenge. These impossible galaxies aren't just outliers, they're signposts pointing toward gaps in our understanding. Whether they reveal new physics, hidden cosmic histories, or just how much we've underestimated the universe's creativity, one thing's clear: the early cosmos was far more inventive than we ever dreamed. And as JWST peers deeper, we're not just rewriting chapters of cosmic history, we're discovering the universe had a wild, untold prologue all along. The Big Bang should have left behind a very specific cosmic fingerprint, not just in the afterglow of the cosmic microwave background, but in the chemical elements themselves. Hydrogen, helium, and a trace amount of lithium were forged in those first fiery minutes, a primordial recipe that should be etched evenly across the cosmos. And while hydrogen and helium match predictions almost perfectly, lithium is the universe's rebellious child. There's only about a third as much as there should be, a discrepancy so glaring that it's been dubbed the cosmic lithium problem. This isn't just a tiny rounding error. It's a gap large enough to hint that something fundamental in our understanding of the early universe might be missing. Where could all that lithium have gone? One possibility is that it's hiding in plain sight, locked away in the hearts of stars. As stars fuse hydrogen into helium, they also produce beryllium, which can decay into lithium. But under the extreme temperatures and pressures in stellar cores, that lithium might get destroyed almost immediately, like a snowflake tossed into a furnace. If this process happens efficiently enough, stars could act as cosmic lithium shredders, gobbling up the element faster than it can accumulate. The problem: even accounting for this, the numbers still don't quite add up. Then there's the more exotic solution: unknown physics. The early universe was a seething cauldron of particles and energy, and our models of those first few minutes rely heavily on the standard model of particle physics. But what if there were particles or interactions we haven't discovered yet? Some theorists suggest that hypothetical particles, like certain types of dark matter, could have interacted with lithium nuclei, altering their abundance. Others propose that the laws governing nuclear reactions in the infant cosmos might have been subtly different, skewing the ratios of elements we see today. The stakes here are higher than they might seem. Lithium isn't just a cosmic afterthought, it's a critical piece of evidence for how the universe behaved in its first moments. If our predictions are off, it could mean we're missing a key chapter in the story of cosmic evolution. Future telescopes, like the Extremely Large Telescope, aim to measure lithium levels in the oldest stars, those pristine relics of the early universe that haven't had their chemistry muddied by later generations of stellar explosions. If those measurements confirm the shortfall, it could force us to rewrite the opening pages of the universe's history. For now, the missing lithium remains one of cosmology's quietest but most persistent puzzles. It's a reminder that even the most well-tested theories can harbor gaps, and that sometimes the smallest discrepancies point to the biggest revolutions. Whether the answer lies in stellar physics, undiscovered particles, or something even stranger, this cosmic accounting error might just lead us to a deeper understanding of how everything began. For over a century, physics has rested on a comforting assumption: the laws of nature are fixed, unchanging threads woven into the fabric of reality. The fine structure constant, a mysterious number denoted by the Greek letter alpha, sits at the heart of this belief. This dimensionless value, approximately 1/137, governs the strength of electromagnetic interactions between charged particles. It determines how atoms hold together, how light interacts with matter, even the very stability of the molecules that make up our bodies. Alpha is so fundamental that altering it by just a few percent would make stars incapable of forging carbon, rendering life as we know it impossible. But what if this cornerstone of physics isn't so constant after all? The first hints emerged in the late 1990s when astronomers studying distant quasars made an unsettling discovery. By analyzing the absorption lines in quasar light patterns created when intervening gas clouds absorb specific wavelengths, they noticed something odd. The spacing between these lines suggested alpha might have been slightly smaller billions of years ago. The difference was minuscule, about 1 part in 100,000 over 10 billion years, but the implications were seismic. If alpha varies, then the very rules of chemistry, atomic physics, and quantum electrodynamics could evolve over cosmic time. It would mean the universe plays by different rules in different eras, like a game where the laws quietly change as the clock runs. Skeptics were quick to pounce. Measuring alpha across such vast distances is fraught with uncertainties. Intervening gas clouds might have unusual chemical compositions. Telescope calibration could introduce subtle errors. Even the expansion of the universe might warp spectral lines in ways we don't fully understand. But then came the clincher. Independent teams using different instruments and methods began reporting similar anomalies. In 2020, a study of light from a quasar 13 billion light-years away found alpha differing by another tiny but statistically significant margin. Meanwhile, lab experiments with atomic clocks, devices so precise they could detect a drift as small as 1 second over the age of the universe, started placing tight constraints on how fast alpha could change today. The results were contradictory, some suggesting no variation, others hinting at shifts. Theoretical physicists scrambled to explain how alpha could vary without unraveling reality. One compelling idea ties it to dark energy, the mysterious force accelerating cosmic expansion. If dark energy interacts with electromagnetic fields over vast timescales, it might subtly tweak alpha's value. String theory offers another wild possibility. Alpha could depend on hidden extra dimensions, their unseen geometry shifting as the universe expands. Even more radically, some models propose that the speed of light or the charge of an electron, both embedded in alpha's definition, aren't truly constant but evolve in concert to preserve observed physics. What's at stake isn't just academic curiosity. If alpha varies, it could explain why the universe seems bizarrely fine-tuned for life. Perhaps the constants we measure today aren't arbitrary. They're the frozen values of a deeper, dynamic process that naturally settled into life-friendly parameters over billions of years. Future experiments might settle the debate. Next-generation telescopes like the Extremely Large Telescope will scrutinize quasar spectra with unprecedented precision. Ultra-stable atomic clocks in space could detect minute changes over decades. For now, the fine structure constant remains both a cornerstone of physics and its most tantalizing loose thread. Whether it's truly constant or quietly evolving, this humble number holds the key to one of science's deepest questions. Are the laws of nature set in stone, or are they merely the current verses in an ever-changing cosmic song? The Milky Way appears serene from our vantage point, a glittering spiral of stars slowly turning in the cosmic dark. But hidden in its ancient starlight lies a violent secret. Our galaxy is a cannibal, growing over billions of years by tearing apart and absorbing smaller neighbors. Astronomers call this galactic archaeology, and the evidence is etched in the motions and compositions of stars that shouldn't be here. One of the most dramatic examples is the Gaia-Enceladus merger, a cataclysmic event that reshaped our galaxy roughly 10 billion years ago. Named after the European Space Agency's Gaia spacecraft that uncovered its traces, this ancient dwarf galaxy was once a separate entity, a collection of perhaps 1 billion stars orbiting the young Milky Way. But gravity had other plans. As Gaia-Enceladus spiraled closer, tidal forces stretched it into stellar streams like Cosmic Tapestry before the Milky Way's core devoured it whole. Today, its remnants survive as a distinct population of stars orbiting backward in the galactic halo, their unusual chemical signatures betraying their foreign origins. These mergers aren't just cosmic destruction, they're creative forces. When galaxies collide, the shockwaves compress vast clouds of gas, triggering fireworks of new star formation. Imagine two crowds merging in a plaza. The chaos creates pockets where people cluster tightly, just as galactic collisions force gas into dense knots where gravity ignites stellar nurseries. The Gaia-Enceladus event likely sparked a frenzy of star birth, seeding the Milky Way with generations of suns whose light still reaches us today. But Gaia-Enceladus isn't the only victim. The Sagittarius dwarf spheroidal galaxy, discovered in the 1990s, is currently being torn apart, its stars smeared into a looping river around the Milky Way. Then there's the suspected Kraken merger, an even earlier collision whose ghostly traces are buried in the motions of globular clusters. Each of these events left behind stellar fossils, groups of stars moving in unison like strangers who still remember their homeland. What's astonishing is how these mergers fine-tuned our galactic environment. The influx of fresh gas and stars didn't just build the Milky Way's bulk, it enriched its chemistry, scattering heavier elements forged in distant stellar cores. Without these violent encounters, our galaxy might have remained a bland, gas-poor backwater, incapable of forming the diverse planetary systems we now find orbiting other stars. Even our solar system's position, safely distant from the chaotic core, might owe itself to these ancient rearrangements, yet the feasting isn't over. The Large Magellanic Cloud, a satellite galaxy visible from the southern hemisphere, is on a collision course. Simulations suggest it will plunge into the Milky Way in about 2.5 billion years, sending shockwaves through the galactic disk. And further out, the monstrous Andromeda Galaxy looms, destined to merge with us in 4 billion years, a final act of cannibalism that will reshape both galaxies into something entirely new. These events remind us that galaxies aren't static islands but dynamic, ever-changing ecosystems. Every time astronomers discover another stellar stream or oddball cluster, they're piecing together a biography of violence, a story where the Milky Way, like all great spirals, was built on the bones of the smaller. And somewhere in that chaos, among the borrowed stars and stolen gas, the conditions for our existence were forged. We're not just inhabitants of this galaxy. We're the legacy of its hunger. Every story has an ending, even the universe's. Billions of years from now, long after the last stars flicker out and galaxies vanish over the cosmic horizon, what fate awaits reality itself? The answer hinges on a single, elusive force, dark energy, that mysterious pressure accelerating the universe's expansion. Its true nature could lead us toward one of 3 possible finales, each more dramatic than the last. First, there's the heat death or big freeze. If dark energy remains constant, as Einstein's cosmological constant suggests, expansion will continue indefinitely. Galaxies beyond our local group will redshift into invisibility, their light stretched beyond detection. Star formation will cease as gas clouds grow too diffuse to collapse. Over trillions of years, even black holes will evaporate via Hawking radiation. leaving behind a vast, featureless void where temperature differences vanish entirely. The universe won't explode or implode, it'll fade into a whisper, a state of maximum entropy where no energy can be harnessed, no structures form, and time itself loses meaning. But what if dark energy isn't constant? Some theories propose it could strengthen over time, leading to the Big Rip. In this scenario, the repulsive force grows so dominant that it overcomes all other interactions. First, galaxy clusters would tear apart, then individual galaxies. As the acceleration intensifies, stars would be ripped from their orbits, planets shredded from their suns. In the final moments, even atoms and nuclei would be torn asunder, space-time itself rupturing at the quantum level. The universe wouldn't just end, it would dissolve into a sea of disconnected particles, each isolated by infinite, ever-growing distances. Then there's the wild card, the Big Crunch. If dark energy weakens or reverses, gravity could regain control, pulling everything back together. Expansion would slow, halt, then reverse as galaxies rush toward each other in a mirror of the Big Bang. Temperatures would soar as matter compresses, light blue shifting into gamma rays. The universe might collapse into a singularity, a cosmic reset button potentially birthing a new cycle of expansion in an endless loop of big bangs and crunches. The stakes couldn't be higher. Current data from supernova and the cosmic microwave background slightly favor the heat-death scenario, but uncertainties linger. Is dark energy truly constant, or does it evolve? Could quantum fluctuations in a vacuum eventually spawn a new universe, even in the depths of heat-death? The answers lie in measuring the universe's expansion with ever greater precision, tracking how dark energies push changes over billions of years. Whatever the outcome, these aren't just abstract speculations. They're reminders that the universe is a dynamic, unfolding story, one where the final chapter remains unwritten, waiting for us to decode its clues. And in that uncertainty lies a profound truth. Even as we ponder the end, we're part of the extraordinary middle. A fleeting moment where the cosmos is alive with light, structure, and the possibility of understanding. From the cosmic web's sprawling filaments to the ghostly whispers of dark matter, the universe has unveiled 30 of its most astonishing secrets, each one reshaping our understanding of reality. We've traced the invisible threads binding galaxies across unfathomable distances, marveled at the quantum foam's turbulent dance beneath spacetime's calm surface, and stood awestruck before black holes that bend the rules of existence itself. Yet with every revelation comes a humbling truth. These discoveries are just the first brushstrokes on a canvas that stretches beyond imagination. Think about how far we've come. A century ago, we believed the Milky Way was the entire universe. Today, we map the gravitational ripples of colliding black holes and decode the faint afterglow of creation itself. But here's what's exhilarating. We're not scratching the surface anymore. We're peeling it back layer by layer, revealing a cosmos more intricate, more dynamic, and more mysterious than anyone dared predict. The anomalies we can't yet explain, the missing lithium, the axis of evil, the impossible early galaxies aren't failures of science. They're invitations to dive deeper, to question bolder, and to rewrite the textbooks once more. Technology is our torch in this cosmic dark. Telescopes like James Webb and future observatories like the Laser Interferometer Space Antenna will push further into the unknown, probing the birth cries of the first stars and the gravitational symphony of merging supermassive black holes. Quantum computers might simulate conditions at the Big Bang itself, while AI sifts through petabytes of data to find patterns no human eye could spot. The next decade could unveil answers, or more thrillingly, questions we haven't even thought to ask. So where does this leave us? Not at an ending, but at a threshold. Every time we solve one cosmic riddle, another emerges, grander and more perplexing than the last. That's the beauty of exploration. The journey never truly ends. Whether it's the hunt for Planet 9, the decoding of fast radio bursts, or the search for life beyond Earth, the universe keeps its greatest secrets just beyond our reach, urging us forward. If these mysteries ignite your curiosity as they do ours, join the conversation. Which cosmic enigma keeps you up at night? The phantom pull of the Great Attractor. The holographic universe's dizzying implications. Drop your thoughts below. We read every comment. And if you want to dive deeper into the wonders of space, hit like and subscribe for more journeys to the edge of understanding. Until then, remember, the night sky isn't just a spectacle. It's the ultimate mystery novel, and we're all turning the pages together. Keep looking up, stay curious, and never stop wondering what's out there. The cosmos has only just begun to share its secrets.